Write a web crawler in 5 lines. Take a URL, download the page, find the links, add them to a queue, repeat. Congratulations! You've just built something that will get your company's IP address banned from the internet within an hour. Because here's what that naive loop actually does. It hammers one poor website with thousands of requests a second. That is a denial of service attack, and you are the attacker. It follows a link into an infinite calendar that generates next month forever and never comes back. It downloads the same page 10,000 times because 1,000 different URLs all point to it. And it never notices that the page it crawled yesterday already changed. Design a web crawler looks like the easiest system design question there is. It's a loop and a queue. It's actually one of the hardest, because the real problems were never about downloading. They are politeness, not destroying the sites you visit; deduplication, not drowning in the same content; and prioritization, crawling the important, fresh pages first out of billions. The single most important structure in the whole design is called the URL frontier, and it is far more than a queue. Get the frontier right, and everything else follows. Clarify first, because crawler means very different things. A search index crawler, a targeted scraper, and an LLM training data harvester are 3 different systems. Functionally, start from seed URLs, download pages, extract links, follow them, store the content, respect robots.txt, and recrawl for freshness because pages change. The clarifying questions that signal seniority, HTML only, or JavaScript rendered pages too, because rendering needs a headless browser and costs 10 times as much. One-time crawl or continuous forever. Continuous is much harder. And the scope, the whole web or a set of domains. Now the constraint that shapes everything, and you must say it out loud, politeness and throughput pull in opposite directions. You want thousands of pages per second globally, but you may hit any single domain only once every few seconds. High global throughput, low per domain throughput, those 2 facts fight each other, and resolving that fight is the entire frontier design. Lock the requirements. Politeness is sacred. Dedup and prioritization are the game. Freshness matters, and it all runs across a fleet. Let's size it before we design. Do this math out loud, and you've already separated yourself from most candidates. Say the target is 1 billion pages, crawled over 30 days. 1 billion divided by 30 days, divided by 86,000 seconds a day, is roughly 400 pages per second, sustained. And you should provision 2 to 3 times that for peak, so call it 1,000 pages per second. Now storage. At an average 100 kilobytes per page, 1 billion pages is 100 terabytes of raw content. And if you keep history and versions for freshness, that's petabytes. 100 terabytes is object storage territory, not a database. Next, the frontier itself. 1 billion URLs, each with a few hundred bytes of state, priority, next crawl time, retry count, is hundreds of gigabytes. That does not fit in memory, so the frontier must be disk-backed. And finally, the scene set. Across all the links you discover, you'll encounter tens of billions of distinct URLs, and you need to answer, have I seen this before, billions of times a second. A hash set of tens of billions of URLs would need terabytes of RAM. Impossible. That single number is what forces the Bloom filter will get to. 3 numbers, 3 storage decisions. That's the whole point of the estimate. Here's the architecture as a loop of components. The URL frontier is the to-do list of what to crawl next, the heart, and we'll open it up in a moment. The fetcher downloads the page, respecting robots.txt and politeness. The parser extracts text and links from the HTML. The Dedup stage checks. Have we seen this URL? And have we seen this content? Storage saves the content to a blob store and metadata to a database. And the newly discovered links flow back into the frontier. The loop closes. Now 3 design decisions that separate senior from junior. First, the DNS bottleneck almost nobody mentions. Every single fetch needs a domain to IP lookup, and DNS can take tens to hundreds of milliseconds. At 1,000 pages a second, synchronous DNS resolution becomes your bottleneck before bandwidth ever does. So you need a DNS cache and asynchronous resolution. Second, 3 stores for 3 jobs. Page content goes to a blob store like S3. The frontier and scene set go to a disk-backed log-structured store like RocksDB, built for high write throughput as billions of URLs churn. And the link graph goes to a database for prioritization and freshness. Third, backpressure. Fetching is network-bound, parsing is CPU-bound, storage is I/O-bound. They run at different speeds, so you connect them with queues and apply flow control. If the parser falls behind, the fetchers must slow down, or your queues grow unbounded and a node runs out of memory. This is the heart, so we go slow. The frontier decides what to crawl next, and it must satisfy 2 goals that directly fight each other. Priority, crawl important, fresh pages first, and politeness, never hammer one domain. Here's why a single queue cannot do both. If you order the queue purely by priority, then a single high-priority domain with 1 million URLs sits at the front and you hammer it. Politeness, broken. If you order it to spread domains out for politeness, you can no longer pull the most important pages first. Priority, broken. 1 queue, 2 goals, and they're mutually exclusive. The classic solution is the Mercator design. 2 layers of queues. The front queues handle prioritization. There's a set of them, 1 per priority level. A prioritizer scores each incoming URL by importance and change rate and drops it into the matching front queue. Higher priority front queues get pulled more often. The back queues handle politeness, and this is the clever part. Each back queue maps to exactly 1 domain. Every URL, for example, .com, goes to the same back queue. Between them sits a router that moves URLs from front queues into per-domain back queues. Now, the mechanism that makes politeness actually work, the timing table. Each back queue has an entry that says, "Do not touch this domain again until time T." A pool of worker threads each pick a back queue that is ready, meaning its next allowed time has passed. Fetch 1 URL, and then push that domain's next allowed time forward by its crawl delay. So even if example.com has 1 million high-priority URLs waiting, they drain out 1 every few seconds from its single back queue, while thousands of other domains' back queues are being crawled in parallel. That is how you get high global throughput and strict per-domain politeness at the same time. Massive domain parallelism. Your real throughput is bounded not by bandwidth, but by how many distinct domains you can crawl at once. 2 more things the frontier must handle. Robots.txt. Before crawling any domain, fetch and cache its robots file, honor disallow and crawl delay, and cache it with a TTL so you're not refetching it constantly. And durability. 1 billion URLs don't fit in memory. So the frontier is disk-backed and sharded by domain hash, which conveniently puts all of 1 domain's URLs and its politeness state on the same shard, so enforcing the crawl delay never needs cross-node coordination. Drawing the front queue, router, per-domain back queue structure and explaining why 1 queue can't do both. That is the single most impressive thing you can do in this interview. The naive loop drowns in duplicates two different ways, and both need solving. The first is URL dedup. Have I already queued this URL? With tens of billions of distinct URLs, a hash set in memory would need terabytes of RAM. We establish that in the capacity estimate. The answer is a Bloom filter. A Bloom filter is a probabilistic membership structure, a big bit array, and a handful of hash functions. To add a URL, you hash it several ways and set those bits. To check it, you hash it and see if all those bits are set. It answers, have I seen this in tiny fixed memory? A few gigabytes for billions of URLs instead of terabytes. But there's a catch you must name. False positives are possible, false negatives are not. It may occasionally say seen when you actually haven't, which means you'd skip a URL you never crawled. It will never say not seen for something you have. For a web crawl, missing a tiny fraction of pages is completely acceptable in exchange for making the scene set fit in memory at all. Choosing the Bloom filter and stating that false positive trade-off out loud is the senior move. Most candidates either don't know it or forget to mention the cost. The second kind of duplication is content dedup. Different URLs, same page. Session IDs, tracking parameters, and mirror sites mean thousands of distinct URLs return identical or near identical content. Downloading and storing all of them wastes most of your capacity. 3 fixes in order of when they act. First, URL canonicalization. Before you even fetch, normalize the URL, strip tracking parameters like UTM source, lowercase the host, resolve relative paths, and honor the rel canonical tag. That collapses all the query string variants into one URL up front. Second, exact content dedup. After fetching, hash the content with something like sharding and check whether you've stored that exact hash before. If so, drop it. Third, near duplicate detection. For pages that are almost but not quite identical, techniques like SimHash or MinHash produce a fingerprint where similar documents get similar fingerprints, so you can cluster and skip near-dupes. Mentioning near-dupe detection, not just exact hashing, is a strong signal. It's a genuine web-scale problem. And then there are crawler traps, the infinite calendar that generates next month links forever, or infinitely deep URL paths. Defenses: cap crawl depth per domain, cap total pages per domain, and flag suspicious patterns like exploding URL length. Naming traps shows you've thought about the adversarial web, not just the happy path. Let's make it concrete. Follow one URL through the system, then break it at every stage. This is how a staff candidate proves the design holds. A new link, example.com/article, is discovered by the parser. Stage 1, dedup. We hash it into the Bloom filter, not seen, so it proceeds. Break it. What if the Bloom filter falsely says seen? Then we silently skip a real page, acceptable by design. Stage 2, canonicalization. We strip its tracking params so all variants collapse to one. Stage 3, the frontier. The prioritizer scores it, and the router drops it into example.com's backqueue. Break it. Example.com already has a million URLs queued. Fine, they drain politely one at a time. The flood is contained to that one backqueue. Stage 4, the fetcher waits until the domain's next allowed time, checks the cached robots.txt, resolves DNS from cache, and downloads. Break it. The fetch time's out. We retry with back off. And after max attempts, we drop the URL. We don't wedge the queue. Stage 5, content dedup. We hash the downloaded HTML. If it matches a stored hash, we discard it instead of storing a duplicate. Stage 6. Storage. Content to the blob store, metadata and links to the database, and the new links loop back to Stage 1. Every stage has a failure mode, and every failure degrades gracefully instead of taking the crawler down. That walkthrough is what defending the design looks like. Now scale it across a fleet and keep it fresh. Distribution. Shard the frontier by domain hash, so each crawler node owns a set of domains, which again keeps that domain's politeness state and back queue local to one node, so no cross-node coordination is needed to enforce the crawl delay. Nodes scale horizontally, and a coordinator or consistent hashing assigns domain ranges, rebalancing when nodes join or leave. Freshness. You cannot recrawl a billion pages uniformly, so prioritize by estimated change rate. A news homepage changes hourly. A 10-year-old blog post never does. Track each page's observed change frequency and set its recrawl interval adaptively. Crawl often what changes often, rarely what's static. That's the freshness versus cost trade-off. And adaptive recrawl is the staff answer. JavaScript rendering. Many modern pages are near empty HTML plus JavaScript, and rendering them needs a headless Chromium at roughly 10 times the CPU and memory of a plain fetch. So you classify cheap fetch for static pages, expensive render only when a page actually needs it. Rendering everything would blow your entire compute budget. And politeness at the IP level. Many domains can share one IP on shared hosting, and one domain can span many IPs behind a CDN. So true politeness sometimes means rate limiting per IP, not just per host name. A subtle point that lands well. Here's the twist that makes you sound current, and it's a real 2020s shift. Since GPT-3, Common Crawl and crawlers like it became the backbone of large language model training data. The web is now crawled not just to index it for search, but to train models on it. And the web is pushing back. Sites increasingly block AI crawlers by name in robots.txt, GPTBot, ClaudeBot, CCBot, and studies tracking the top million sites show AI crawler restrictions climbing steeply since 2023. The subtle part, a staff candidate names, robots.txt now distinguishes training access from search access. A site may allow the search bot that sends it traffic while blocking the training bot that doesn't. So a modern ethical crawler must identify itself honestly with a proper user agent string and honor these finer-grained, purpose-specific directives. And that shades into the anti-bot arms race. Rate limiting, captures, fingerprinting. The ethical line is clear. A legitimate search or research crawler stays polite, identifies itself, and honors robots.txt rather than evading defenses. Saying that line out loud separates a real crawler from an abusive scraper, and knowing the training versus search distinction is a genuine 2026 signal. Let's zoom out. A crawler is a politeness, dedup, and prioritization problem, not a download loop. The URL frontier is the heart. Mercator's front queues get priority right, back queues get per domain politeness right, and a timing table enforces the crawl delay. Respect robots.txt always, and in the AI era, honor the training versus search distinction. Use a Bloom filter for URL dedup and accept its false positive trade-off. Keep the frontier and scene set in a disk-backed store. Deduplicate content with canonicalization, hashing, and near-duplicate detection, and defend against crawler traps with depth and page caps. Shard by domain hash, so politeness stays local. Recrawl adaptively by change rate. And remember the DNS cache and backpressure between stages. Master those, and you can design a planet-scale crawler and defend every edge case. But knowing it and performing it under pressure are different skills. Practice this exact interview with an AI interviewer that pushes back like I did at crackit.io, free. Design the system, then go defend it. See you in the next one.